This is 4 charges in 2 dimensions. So this problem we have 4 charges on an xy axis. Draw that like this. Here's x, here's y. We have 1 at the origin. We have 1 at the position x equals a distance a away. We have another one at y equals a, so another distance a away. And then we have 1 at x equals a, y equals a, like that. So 4 charges sitting on a square. So we're going to label them 1, 2, 3, and 4. And we're going to look at their magnitudes. They all have the same magnitude of charge. This one is plus q, this one is plus q, this one is plus q, and this one is minus q. So the question is, what is the force on the 4th charge, on charge 4, due to the other 3? Okay. So we can write it this way. We know that the forces will just add. So F4 is F1, 4. So that notation means the force of charge 1 on charge 4 plus F2, 4 plus F3, 4. Okay. So all we have to do is use Coulomb's law to figure out what each one of these forces are. So let's start with F3, 4. Okay? So we know according to Coulomb's law, we'll get a force along this axis, which is just the x-axis, and it will be repulsive because they're both positive, so F3, 4 will look something like that. And we can write it down here, F3, 4 equals, start Coulomb's constant, Ke, times the charge of one and the charge of the other, so that's q squared, big Q squared, over the square of the separation, which in this case is just a. These are on a square, so it's a all the way around. So over a squared. And then the last part of Coulomb's law is r hat, and that just means the unit vector and the direction of the force. So in this case, that's the x-axis, so that's what we call I hat. Remember, the unit vector in x is I hat, and then y is j hat. There's F3, 4. F1, 4, pretty much the same thing, except along the y-axis. So the force that 1 applies to 4 is also Ke. The charges is q times q, q squared. The separation is a squared, over what? Oh, not over. Times the unit vector is j hat, because it's in the y direction. Okay, so we have 2 of our forces already. We have F3, 4, and we have F1, 4. Now we have to get the one that's slightly harder, F2, 4. Okay, so it's going to be Ke, we know that. The product of the charges, it's minus q times q, so it's actually going to be minus, okay, better. So there's your minus sign, and there's your q squared, over the separation squared. So these aren't separated by a, but we can use Pythagorean theorem to know that they're separated by the square root of 2 times a. Square root of a squared plus a squared is square root of 2a squared, square root of 2 times a. But that gets squared in the denominator of Coulomb's law, so that's 2a squared. Okay. So that's the magnitude of the force, but now we need the direction. Well, here's the axis between the 2 charges. We know that it's going to be along that axis. That's the positive direction, but it's negative. It's attractive. So it's going to be something like this. So how do we describe that direction? Well, we could just make up a new unit vector. We have I, j, k, z. We could call it L hat or something and say it's along this direction. But the problem is we need to add these vectors. So we really have to get their components on the same coordinate system. We have to get these 2 are in terms of x and y components, so we have to write this one in terms of its x and y components. We can't call it L hat or diagonal hat or whatever you might want to call it. So I've written this here with some room, because what we're going to do is just look at it and say its x component is this way, and we know that this is 45 degrees for the diagonal of a square, because there's a right triangle here. So it must be minus the magnitude times the cosine of 45 degrees, because there's the x component. So minus that times cosine 45 degrees I hat, and be minus k e the same magnitude q squared over 2a squared sine 45 degrees j hat. So that's the force. And the y component also will be negative, also will be at 45 degrees. Okay. So we know the sine of 45 and the cosine of 45 is the square root of 2 over 2. So we can simplify this sum. This would be, let's see, that's square root of 2 over 2, so that's going to be square root of 2 over 4. It would be minus square root of 2 over 4 ke q squared over a squared I hat, and then the same term, minus square root of 2 over 4 ke q squared over a squared j hat. So there's F24, about as simple as we can make it there. So for the final term, F4, the big force, we just add these up component by component. Okay? So let's look at F4. See what we get. Let's see. So in terms of the x components, it looks like F34 has an x component. It has one here, and we've now written it in the same ke q squared over a squared. So this is 1 times that. This is minus square root of 2 over 4 times that. So we can write 1 minus square root of 2 over 4 ke q squared over a squared I hat. And then the exact same thing happens in the y direction. We have a ke q squared over a squared times 1, and then a minus square root of 2 over 4 ke q squared over a squared. So this is plus basically the same thing again. 1 minus square root of 2 over 4 ke q squared over a squared j hat. And that actually is the answer. That is the force. Now what's a good idea in these problems is to look at it and see if it makes any sense. Right? We know that we have these two on the axis. This one is down at an angle because it comes down because of negative and positive. But is it right that we're going to sort of get something that looks like this? Well, we can kind of look at this and do the vector addition in our head, right? So if you have a component this way and that way and you add those, it's going to be a big vector going this way. But then that's going to get canceled some this way, but not completely canceled because these two are bigger, right? Because their charges are closer. So this diagonal force of 3 and 1 is going to be bigger than the one of 2. So the net force we know is going to be something like this. Big F will look something like that. And that's indeed what we have. So we have 1 minus something smaller than 1. Right? Square root of 2 over 4 is, I don't know, less than a half. So we get some number lower than 1, some number lower than 1, but you get something positive x and y, and it's less than 1 because these represent 1. Right? So these represent a full k q squared over a squared. And it's less than 1 because this one pulled it back. So pretty much the answers do match the diagram you would imagine in your head.